So they're looking at modifying this existing system so it's even more user-friendly and is accepted. Another biochar type of one, in this case, it's done at a community level. So rather than at an individual or small cluster of homes, what they're looking at here in Nairobi, in fact, is a way of taking on board through a pyrolysis process. So this is, it's sort of burning in the absence of oxygen, so you produce a charcoal, if you like, material for sequestering carbon dioxide and then taking that back out into agriculture. So there's a community scale sort of an option there being looked at. So that just gives you a snapshot of some of the sort of technologies that are, in essence, available but not configured for, if you like, more sustainable sorts of toilets. But what do we have today? Well, you've got committees that are well up on what's available, but maybe not everyone has sort of seen it all packaged together, so I'll just quickly go through this. So what I've listed here are the sorts of toilets. So we don't all know about flushing toilets. In countries like in Australia, where I come from, you cannot buy what you would call a conventional flush toilet. They're all dual flush. So for a number 1 or number 2 job, if you want to call it that, a different volume of water. So you may be using less than 1 to 3 litres, we're talking litres, sorry, or less than about half a gallon for the urine side, and a bit over a gallon for a half or 2, depending on the style for the fecal flush. So dual flush type toilets are now, if you like, mandated. They're the only ones you can buy in Australia. If you go to a Home Depot or whatever, that's the option you have. But there are a huge number of manufacturers of those sorts of toilets. So you can see the amount of water used, so I won't go through that. It's widely accepted, but there's a lot of water used. Vacuum flush toilets, which is what that little photograph is of, you can either have standing pedestals or wall-mounted ones. These are like what you have on board aircraft. They use air as the transport rather than water. And so the beauty of these are that you can retrofit into existing homes. You don't rely on gravity. You can take the sewage or the fecal material up and urine up and down before you go to some sort of collection place or connect it into an existing vacuum or pressure sewer system. So they use a lot less water. There's more noise associated when you flush the toilet, slightly more expensive. Then there are, of course, the urine diversion sorts of systems, which I'll show you some bigger photos so you can see them more easily in a minute, using a lot less water in some cases, to no water. There are various configurations of those. Of course, then there are the dry and foam flushing types of toilet, composting toilet systems that are available. You sort of see some of the pros and cons of there. No water is used, but there's a slightly bigger space requirement, but that often is not an issue. There's a slightly higher level of maintenance because at some stage the residuals need to be taken out of there. If you're using the foam, you need to maintain the foam in the flushing mechanism. So there's a slightly greater human intervention, if you like, than you would have in a normal toilet perhaps. And then last of all, for the blokes here, as we say in Australia, the males in the audience who are used to urinals, there are waterless urinals, and of course there are many manufacturers, but the innovation that is current, is a bit hard to see, is the little diagram on the right. So rather than having this liquid that is lighter than urine, which has to be replaced every year or so in the waterless urinals, which stops the foul odours coming up from the sewer, if you like. A new invention here, which is much more sustainable, is simply, a bit hard to see, there's a little grill where the urine goes down, and then there's basically a strip of like plastic hose that's folded on itself. So when the urine goes through, it opens it up, and when the urine stops flowing, it closes itself off through capillary reaction. And so it stops the foul odours coming back up. It's a much simpler, more robust system than the currently available waterless urinals that are available in this country, for example. So that's a German invention. So the sorts of so they're the toilet options. So the sorts of sanitation options, then we can start looking at zero discharge waters. So we can go from the dry to wet flushing toilets. When I say wet flushing, I mean flush type composting toilets, which actually use a solid liquid separator. So you can still have a conventional looking toilet connected to a composting system, say in your basement of your house. And I'll show an example of that. So that's at the lower tech end. At the higher tech end, there are groups in Germany, for example, that are building into houses membrane bioreactors, and some of this work's been looked at in Australia also. So this is a reactor which takes more energy and maintenance, but it could be managed by an external agency. In fact, it should be probably managed by an external agency rather than the homeowner. That basically treats that water, and it could treat it through to a non-potable level for toilet flushing and clothes washing and garden irrigation, or in the case in Germany where they're talking about the Loo Loop, as they call it, where they basically take that water through a process that actually makes it fit. Well, in that case, they send it back to the toilet, and then they have next to the Loo Loop, so that's the toilet water goes through a membrane bioreactor, and the clean residual of that, which looks like normal water, is used for flushing. Then they talk about the Blue Loop in the house, which is the grey water going through a membrane bioreactor, and that water is so easy to treat and so well treated in the German scenario that can be used as drinking water as well as for other uses in the home. That can actually make your house then totally self-sufficient with just some topping up coming from rainwater when that's available. So you can make your house totally off the grid with available technology today if you want to go down the high-tech option. But you can see some of the benefits here, the non-toilet systems, the low-tech and the high-tech. So there are a range of options that we have at our fingertips today, and this is the point of these demonstrations. So I would encourage this community to embrace the idea of having demonstrations and have them on board in your own homes. We're not going to necessarily pick the best solutions for everyone straight away. That's the idea of demonstrations, is to learn from them. So we need as a community to accept that. And in the jargon here, we talk about adaptive management. So we learn from these experiences and we adapt to what's going to fit and work in this community.
Yes.
So from the toilets you've just seen and the sanitation options listed here, this is the foundation of what I want to contribute to your discussion. Thinking about, well, what are the options you'd like to try in this community? And the rest, I just want to say, well, this needs to be not looked at an individual home basis. Of course, we need to look at this as a whole community and how does this fit back into this broader sustainability picture. So the idea here is that we need to be thinking about these demonstrations within that broader picture. So it's not just to solve the nitrogen problem. I keep coming back to that just to beat that poor dead horse, I guess, but just to make that point. And in so doing, I want to just leave you with a couple of more systems. So from a community point of view, what are some of the potential systems that we might have here? So I want to talk about one which has, it's not using drinking water for firefighting. And I'll show you how we get around that. Using black water only into a sewer, which may be the existing sewer in the small part of Falmouth where you already have that, but relining it and having it really as a much smaller vacuum or pressure sewer, potentially, and putting in perhaps the smaller pipe, which is much less expensive and much less leaky, into other high-density areas is an opportunity you might want to consider. So that is a type of sewer scenario, but it's not your conventional sewer by any means. It's going to what I'll call an energy recovery station. So the black water is going in that sewer only, capturing the nutrients and the energy. The grey water being treated locally at the household or cluster household level of non-potable reuse. So I'll give you an example of that, and then I'll give you one other example and then let you fire away with your questions. Now, it's a bit hard to see, but here's an example of a house in a community. So it could be considered in part of the higher density area of this region, for example. So in this house, if I can get this pointer to work, I'll start with where we are. So we currently have drinking water available, but in this house we'll use less than 20% of the conventional household drinking water needs. And the reason is because we've got loops inside this house. So drinking water comes in for your kitchen and bathroom needs, but your food waste disposal unit and your toilet or toilets are connected to a black water sewer, which could be gravity or could be vacuum or pressure in the house, depending on the lay of the land, so to speak. It could all still be through gravity systems. So you don't need to change your toilet for this system. You can still use an existing toilet potentially. But only connecting that toilet and food waste to the new type of sewer, which again could be a gravity sewer on some areas, or may make more sense to have a pressure or vacuum sewer going to, and this is an issue of scale, something like 1,000 or so houses may be needed to make this worthwhile. It could go up to several thousand potentially, to an energy, I'll call it a recovery station. So in this station we turn that organic carbon in the black water back into electrons when required into the grid, and the residual from that process is fertilizer. So it contains those nutrients that I've been talking about. It will also, depending on the process used in this black box, it could produce a pelletized material, which is pretty clean fertilizer, or it could produce a black liquor, which contains a range of other organics, which would need to check on where that fertilizer is going as to whether that is a safe way of dealing with that back out into agriculture. And if we do that, then the rest of the water use is grey water. So the grey water goes down through a heat recovery, because the grey water is the hotter water in your house. You capture that energy, you treat that grey water, and the reason for treating it is because we want to use this back in the house. So we need to treat that grey water, otherwise not only will it go smelly after 24 hours, it may be unhygienic because of pathogens as well being present in it. So we treat it, and then we can reuse that back in the clothes washing machine. We can use it for flushing the toilet. We can use it for irrigating the garden outside. And we can capture rainwater off the roof to top up this system. And the hot water system makes use of this heat recovery with a heat pump. Preheat, we could have a solar thermal up here for preheating the hot water as well. Or we could have solar cells for electricity production. And how we deal with firefighting, this needs a lot of discussion with obviously the firefighting union and people involved associated with firefighting. But there is developing technology which is still at the research implementation stage that makes use of electrostatic field. So if this is a fire detection system in your ceiling, it doesn't release water, it releases electric field. Because a fire is basically ionized particles, if you put a 600 volt electric field with very low amperage, so it's not going to hurt anyone, it will basically immediately suppress that fire. So firefighters are now looking at using this like a wand. They can go into a burning building and wave this wand in front of them, and the fire will simply be suppressed in front of them. So this is technology, as I said, it's not commercially yet available, but it is well, there are patents out for it, and it's being developed at universities like at Harvard University. So we can think of in the future that our household fire suppression systems are these electrostatic systems, as an example. So we don't need to worry about having water mains to supply firefighting flow, which means ultimately the community water supply systems don't need to be these huge, expensive, big pump systems. They could be small bore, maybe stainless steel pipes, not needing to have that chlorine residual, and therefore no chemical disinfection byproducts in them. So this is why I'm saying it's all part of a bigger picture. I'm moving well out into the future there, but just saying there's an ambition or goal that we could move towards in the long term. So here's scenario A, where we might want to have or do have an existing sewer sort of infrastructure, or the density of homes makes sense to consider a localised sewer for energy and nutrient recovery. Another option, which is in the city of Hamburg, which is being constructed, and there are homes being built. Often they're multi-rise homes because it's a high-density part of the world. But in that part of the world, they're looking at combining the organics from the house along with the feces, so the black water, for local pickup by a truck. So it goes into a storage tank at the house. It then goes in through a composting process to make it safe, and then out to agriculture. And I'll talk a little bit more about the urine side of things, but where the 80% of the nitrogen is actually in the urine stream. So in some cases it may make more sense to have a urine diversion toilet system where you collect that urine at the house, store it, and storing, I've done a lot of work in Sweden on the safety of this, and simply storing for some months, because the way urine is, the pH goes up to about 9.6, and storing for a few months, the pathogens are naturally inactivated just by storing it.